Hey guys, you might have noticed that I'm in a different room. Hopefully the sound and image will work better from your end because we have a faster internet speed in here. I'm just hoping that the glare isn't too bad. I see that there's kind of a pretty significant one there. So I will try to avoid that spot right around there. Okay. So we were talking about conservation laws last time, and that is a general way to break up the universe into a system and environment. And then rather than following forces, we identify a quantity, or we will identify a quantity, which characterizes the system, and the interactions with the environment will cause that quantity to change. So the specific example that we're going to talk about today is so-called impulse and momentum. Okay, impulse and momentum. And the idea is going to be that we will have a system and on the inside of the system, it has lots of properties: mass, color, taste, temperature, and it also has a property called momentum. Momentum is going to be a new quantity for us that characterizes the state of a system. The environment is going to be on the outside, and through interactions, you can add to or take away from the momentum on the inside, and the word for the input and output is going to be impulse. Okay, so this is very similar to the example I gave last time with a bank account or rolls of toilet paper, or I don't know, anything where you have a quantity that is conserved or could possibly be conserved. So the final equation we're going to get to precisely mimics what we had for bank account balances. We're going to find eventually that the change of the state variable, momentum, equals the total or net impulse. So we're going to say change in momentum equals impulse. Okay, so that's how this connects to what we had last time, or that's the way that these ideas are going to connect with what we saw last time. To make this more precise, we need to go back to Newton's laws and rewrite them in an appropriate way. And then so we have to define what is momentum in terms of Newton's laws and kinematic quantities, and what is the impulse in terms of Newton's laws and kinematic quantities. So we have the following. Let's begin with Newton's second law. Let's write that out. So that says F net on a system equals the mass times the acceleration of the system. And these are vector quantities. So what I'm going to do is slightly rewrite this, and what I'm going to do is completely fine for every example that we have solved thus far, but there are some problems that you can have, specifically like a rocket launching and losing fuel with time, where you have to kind of be a little careful. So I'll point that out in a minute. Okay, so I'm going to rewrite this. I'm going to express this as mass times the derivative acting on velocity. No big deal there. And then I'm going to say, assuming the mass is constant, you could for free put it inside the derivative. And you could rewrite this as the derivative acting on a quantity called mv. All right. And we arrive at the desired place. Two things. We're going to give this quantity a name. We're going to call it momentum. The symbol for momentum used, at least in physics, always, is p. And it's a vector quantity because velocity was a vector and mass was a scalar. So momentum, the symbol for momentum is p, and the units of momentum would be kilogram meter per second. So the units of momentum are kilogram meter per second. All right, so this is a new quantity. It's pretty much just the velocity, but it's rescaled by mass. And that kind of makes sense because if you think about everyday use of the word momentum, you'd say, oh, what has a lot of momentum? I have a person walking across the street versus a person running across the street. Well, you would say the person running across the street has more momentum, that because they have a bigger velocity. On the other hand, I could have a housefly traveling at 1 meter per second, or I could have a steam locomotive traveling at 1 meter per second. And I surely would say that the steam locomotive has more momentum, even though they had the same velocities. So that in that case, it's the mass that made the significant contribution. In reality, both are important for having momentum. So I'm going to rewrite this. Our new way to write Newton's second law is that the force on, net force, I should say, on an object equals the derivative with respect to time of momentum. In fact, this is the true way to write Newton's laws. For every example we have solved this year, this is completely equivalent to this. However, if you had a situation where the mass was changing, like in a rocket ship, or I'm sure you can think of some other situations, then F net equals ma is actually not correct. In fact, this is the correct way to state Newton's laws. And then if you say it this way, then it's always true with no caveats. Right. I apologize, I missed my second board, but hopefully the quality of the video and audio is better. All right, I have to find my spot here. Okay, so we have a new version of Newton's second law, which says F net equals the derivative with respect to time of momentum. That's not quite the form that I want, because I want something which says the change in momentum is related to some other quantity, which I'm going to name the impulse. To get to that point, what we need to do is integrate both sides of this equation with respect to time. And just some words. This is called an equation of motion, more generally in science, or in physics, when you're describing an equation which describes how things move. It's called an equation of motion. And at various times, you may multiply the equation of motion by some quantity and then integrate. And so, and the output of that, when appropriate, is some sort of conservation law. And those collectively are called integrals of motion. Energy is going to be an integral of motion. Momentum is an integral of motion. Angular momentum is an integral of motion. That's not how it's usually phrased in Physics 1. It is a little bit in dynamics, but even there, not so much. But if you take more advanced mechanics, that's the type of language they will use. Okay, so with all that set aside, let's do that. So let's integrate both sides with respect to time. So if I integrate on the left-hand side, I integrate on the left-hand side, I get what I get, really. And then if I do the same on the right-hand side, then I end up with the integral of a total time derivative acting on momentum, dt. Now, using the fundamental theorem of integral calculus, and you're probably thinking, good God, I thought I didn't have to know that. Wrong, nothing ever goes away. Fundamental theorem of integral calculus says that the integral of a total derivative is just the change in the quantity being differentiated. So I can write this as the change in momentum. Now, our goal was a statement which said delta momentum equaled impulse. We have arrived at a formula that says delta momentum, therefore, the integral of forces over time will give us the impulse. This, in fact, is the net impulse. It comes, and we get the net impulse because we are integrating the net force. If we had a single force, we could calculate its kind of partial contribution to the total impulse. And we would just call that the impulse of the force. The symbol used for impulse, at least in introductory physics, is usually a J. J is the symbol for impulse. And it has the same units as momentum, so that's kilogram meters per second. Okay. So what does that mean? Impulse equals change in momentum. What is an impulse? Well, it has two things going on. One, you have to have a force, right? If I want to change the momentum of something, so if I wanted to change its velocity or mass, you're going to need some force. Okay, so that's one thing. On the other hand, it has to be a force applied over time. So if you have a force acting on something, but it's not exerted over any time, then, or if if you have a finite force, but you apply it over a smaller and smaller and smaller and smaller and smaller moment in time, then you don't get much change in momentum. That kind of makes sense. So one way to think of it is, if I want to make something move fast, I can either punch it and hit really hard, with all my big muscles I've developed lifting markers for years. So you punch it really hard, and then you don't have to punch it for the time isn't very long. It's just that the force is large. On the other hand, maybe this is more appropriate, I could simply push something with my fingertip, and if I just keep pushing, just keep pushing, just keep pushing, I will push for long enough time, I can actually achieve the same final velocity, same change in momentum. So there are two ways to affect momentum. You could either have a big force, or you could have a smaller force but compensate by applying it for a large amount of time. A long time interval, and the change of momentum is going to be the same. So this is the definition of impulse and momentum.